So, let us take this up further. Okay. So, now I am going to call upon a little bit of your imagination / knowledge of Fourier transforms. What we had was here. I must apologize right away here for the fact that my font has gotten messed up a bit. I am really sorry about that. I did not know, maybe it is the versioning of PowerPoint which did this mess, but I first need to set this right by saying that P here is 2 pi. So, please read this as 2 pi over T, 6 pi over T, 4 pi over T and so on. I will make efforts to ensure that this does not happen as frequently as it is happening now. It is just a versioning issue with PowerPoint, I suppose, going from one place to another. But then, okay, let us come back to the physics and science. So, what we have at the bottom here, this is what came out of the math we had. We have quite a few symbols on these plots. So, let me explain these things to you. I should probably also make another transformation. The W which I have written here with the font that made the W's appear as W's, this is actually omega, the angular frequency. The rest of the slide has the required integrity. So, let us not worry about that. So, here notice the bottom plot. On the horizontal axis we have 2 pi over T multiplied by integers 2 pi, 4 pi, 6 pi, both on the positive and negative side. We have the peaks that we had considered earlier. So, this is the transmittance of the cavity, right. So, now and there is an envelope. All right. So, this is a description of this whatever be the physical phenomenon in the frequency domain. Okay. So, this is the frequency domain description of the transmittance of the echelon, right. Now, we make a jump, we ask the question, since the bottom view graph is in terms of frequencies, when I say that, when I call this the bottom, the bottom half is about frequencies, we can ask what is the function, okay, whose Fourier transform looks like this in the frequency domain. What is the time domain function whose Fourier transform looks like this in the frequency domain. Okay. This is just an exercise in engineering math or math physics. Of course, as my friend here is prompting me, good prompt, thank you. Let us make the simplifying assumption that each of these peaks is Gaussian, because the Fourier transform math of a Gaussian is nice. All right. Let the envelope also looks rather Gaussian to us. So, these are two Gaussians of different widths apparently. Okay. So, now if I now ask the question as to what happens in the time domain, what could have happened in the time domain that led to this picture in the frequency domain, right. We can use all our muzzle of the Fourier transform and then observe the following fact. So, we essentially had a transmission function over here, this set of functions which are like the teeth of a comb, okay, which is what we have written here as the triple I omega tau divided by t, right, multiplied by this triple I function is something that takes care of the fact that this phenomenon repeats every 2 pi over t in omega. Okay. So, this function takes care of the periodicity. Now, this is now multiplied with another function g w, which is the shape of each peak or each line, right. And there is an overarching guy f, f takes care of the envelope f of omega. So, if I remove all this unnecessary tick marks and let me highlight this for you, f of omega is the envelope, g is the line shape. So, this entire thing, right, can be described in terms of three piece functions. Okay. So, that is to say I have this comb sort of function over here which has these teeth. I think it is sometimes referred to as the Shah function, but it has a periodicity. Okay. So, the periodicity of this periodic function is 2 pi over t, and that is essentially here, actually it is not a simple product, it is a convolution with the line shape function. Convolution is a mathematical operation which you have learnt in your math physics or math engineering math with respect to Fourier transforms. So, just for those of you who may want a quick recall, take this Gaussian line shape function and simply sweep it over from left to right and multiply it at every instant with the teeth function over here, right. You would get this. It takes a bit of imagination, but there is plenty of good animation on the World Wide Web which will convince you that this is how a convolution happens. And on top of that, just simply this is just a multiplicative envelope function f of omega. Okay. So, convolution is also sometimes called the folding product. Okay. So, the whole point is that there is a 3-piece description of this transmission function of a real life optical cavity or echelon. Okay. Now, the point being that this, if transformed into the time domain, okay, noting the fact now that if we have the frequency domain and time domain, these are two conjugate domains, a multiplication in one domain is equivalent to a convolution between the corresponding functions in the conjugate domain. If f and g are two functions where f and g are functions of time and capital F and G are functions of frequency correspondingly such that F and G are Fourier transforms of one way or another. So, capital F is the Fourier transform of little f, capital G is the Fourier transform of little g, then the product of f and g in the multiplicative domain is equivalent to a convolution of f and g in the time domain. Likewise, vice versa, a convolution between the two functions in the frequency domain is equivalent to a simple multiplication of functions in the time domain, right. Agreed? So, now let us do the following neat little thing. So, what do I need? If I know that this is the result in the frequency domain, the result at the bottom, this is the description of my Fabry-Perot in the frequency domain, right. This is what is happening inside. Now, I can just do, I mean nothing can be truer in life than mathematics, right. So, if I simply take the math and apply it more or less faithfully, all I must do is the following. I take the function f of omega, find its Fourier transform or its inverse Fourier transform in this case. I go from the frequency to the time domain. So, inverse Fourier transform it, get f, okay. And now get the Fourier transform of G, capital G, or the inverse Fourier transform of capital G of omega, you get G of t, right, agreed, coming along. Now, take the tth function and get its inverse Fourier transform back into the time domain, right. Now, what are the variables of interest? Omega here, t here. Now, there is a capital T which was essentially 2 pi over t dividing omega. This is another frequency quantity with frequency with the units of frequency. So, that omega divided by 2 pi over t is dimensionless. Likewise, there should be a corresponding t, okay, over here, which essentially indicates temporal periodicity and a quantity that has units of time. I am trying to sort of request you to make some intuitive leaps of, you can say, faith or whatever, so that this form motivates us with our intuition in terms of Fourier transforms to hopefully agree upon the fact that if there was an electromagnetic wave or a set of electromagnetic waves with the transmittance having a transmittance across a Fabry-Perot echelon, okay, all of these could be simultaneously present, mode nu 0, nu 1, nu 2, nu 3, nu minus 1, nu minus 2, nu minus 3, all these can be simultaneously present inside the echelon because light waves can interfere, they can coexist, they can share the same space and time in a particular medium, right. Then if they coexisted so as to have this fingerprint of the transmission function, then Fourier transforms tell us that in the time domain I would have likewise the time domain description of the same phenomenon of the same electric fields, okay, would be one where in terms of the time domain it would be one where I had three functions. First of all, I had a function f, little f of t. Now, little f of t is derived out of the spectral envelope, not out of the spectral teeth that are underneath the envelope. Why? Because once again a function that is narrower in the frequency domain is broader in the time domain and vice versa. So, let me jog your memory back to your math physics days and say you know that delta nu, or in this case delta omega, delta t, okay, are 2 pi. If this was nu, this product would be unity, right, in terms of the widths. So, take a Gaussian function. In certain cases you could also have a multiplicative factor depending upon the shape of the function, but this is the time bandwidth product vis-a-vis Fourier transforms, right. So, the function that is broader in the frequency domain results in a narrower feature in the time domain. Okay. This is just visual math. So, the thinner peaks, the narrower peaks in the time domain essentially are arising out of this broad envelope in the frequency domain. Are you with me? Now, the one feature that remains faithful to everything is the teeth function, the function that takes care of the periodicity. Now, recall here that the multiplication in the time domain between the teeth function and the function f should become a convolution, which it has. So, take the function that describes the periodicity and convolve it with this one thin slim function of time which you got from transforming the envelope in the frequency domain. That should make these little time domain, that should make these little time domain, the slim functions f repeat at a periodicity of t all over. Yes, it should, right, because you convolved it with the periodic function t. Now, there was a convolution between g and this teeth function. So, in the time domain that merely becomes a product with respect to this teeth function, so to say. Now, whatever was responsible for the narrower features in the frequency domain, that is the width of g in the frequency domain, the width of the g function in the frequency domain results in the envelope feature in the time domain. Now, for the narrower features, let us use the word pulse. So, each of these are a pulse. In time domain, let us use the word pulse. In frequency domain, let us call these, each of these a peak. So, the individual yet repetitive periodic set or train of pulses in the time domain arose out of the features of the envelope in the frequency domain. Okay. And the individual spectral peaks in the frequency domain arose out of an envelope for these pulses in the time domain. So, they share an inverse relationship. So, what was the whole burden of this discussion? All we now said is that if I now took the resonator modes, which is these peaks in the frequency domain, we took the resonator modes and multiplied it with an envelope which I call multiplied by something else, which is coming out of the real physical aspects of the resonator, then I get a very realistic spectrum of the transmittance, and this, looking at it in terms of Fourier transforms, tells me immediately that this resonator is sufficient to create a finite periodic train of identical pulses. And this course is entirely about pulses. So, this one optical resonator or the Fabry-Perot interferometer, okay, is the mother of all optical pulses in this course, which will, from which very nice physics and technology and science emerges. Okay. So, therefore, this is really a sort of maybe one of the iconic sort of view graphs of this course. We will of course come back to it and sort of unwrap and unpeel this in great detail in this course, but even before proceeding with things further, all I want to convince you is that there is a lot of physics in just this optical resonator, right. People have studied this, investing significant parts of their careers. There have been Nobel Prizes also given for works relating to this, such as the Nobel Prize to Professor Ted Hansch and Professor Jan Hall for frequency combs. So, this is typically a frequency comb, and a little more thought and a lot more thought can prod you on to some insightful questions about this little repetitive periodic function in the time and frequency domains, and this is going to play a really key role. Okay. For example, the invention of the laser itself also had optical resonators at its heart. It was the race actually to build high quality resonators, whether it was a maser or a laser. So, from the Nobel Prize all the way from for Townes and Swallow, all the way down to a relatively recent Nobel Prize to Hansch and Hall. On the way, you can also count in the case of one of the Nobel Prizes given for quantum science and technologies, not the most recent one, but the one earlier to Weinland and Herosh. Herosh's work, Professor Herosh's work was all about superconducting cavities. Again, that has something to do with the quantum nature of light, and the most recent Nobel Prize in attosecond physics also hinges heavily upon these pulses and these remarkable tools of light which optical resonators are. So, that is we could quickly dive into this and get somewhat deep insight using just few facts, okay, 3 facts which I have written down over here. That is, a multiplication in one domain between 2 conjugate variables which are related by Fourier transform, conjugate variables and functions related through a Fourier transform amounts to convolution in the other. A convolution in the first domain, like conversely, implies a multiplication in the companions variables domain, and that there is such a thing as the time bandwidth product.